Hello everyone. So I'm happy to have Dr. Senbei from Boston University to be our second speaker today. And Senbei graduated from University of Science and Technology of China in 2015. And then he got his PhD from the University of Alabama in Huntsville in 2020, working with Gary Zank on the energization and dissipation of plasmas with kinematic simulations. And then he joined Los Alamos as a postdoc after his graduation, and have been working there for 3 years on MHD simulations of magnetic connection and turbulence with Drs. Hui Li and Fan Guo. After that, he joined Boston University as a research scientist. And then he's currently working with the NASA Shield Drive Center, led by Maria Ober, focusing on the study of the outer heliosphere. So he will give a talk about this today. That's it. Welcome, Senbei.
Hey, thanks, Finn and Ima and Jason for the invitation and hosting of the seminar. It's an honor to be here. And it's probably easier for me to sit down. And so I'll be talking about the heliosheath, the plasma physics of the heliosheath today, and this work is supported by Shield Drive Center, and I'll thank the co-authors, collaborators especially from BU, and especially Professor Ralph Ofer for supporting me. And so if you've been working on heliosphere or the outer heliosphere, you probably are somewhat aware of the debate about the shape of the heliosphere, and so that's what these figures are about. And so these are the global heliosphere simulations from different models. For example, the left one is from the Huntsville model, middle one from the Boston University BU model, the right one is from the Moscow group. And so these have somewhat different shapes in the heliosphere, but if you're not familiar with that doesn't matter, since that's not what I'm going to talk about. So what I want to emphasize here is that regardless of the shape of the heliosphere, I think that the region of heliosheath is an interesting region to study the plasma physics within it. And so I listed a few interesting properties of the heliosheath, and I'll go through this in the next few slides. And so first is the pickup ions. So we know that the pickup ions are ionized neutral atoms in the solar wind, and they are usually the energetically dominant component in the outer heliosphere, and that's illustrated on the right figure here. And it shows we can look at the second panel from the bottom. This purple line shows the observations of the pickup ion pressure from the New Horizons data, and the blue line is the thermal ion pressure. And and the black line is the Voyager observations, and it shows that basically beyond about 10 AU from the sun, the pickup ion pressure becomes the dominant pressure terms. And so the heliosheath is no difference. So the pickup ion is the dominant component there. And the pickup ions, the newborn pickup ions usually follows like a ring beam distribution, or this torus-like distribution, and then it's isotropized in the solar wind, but they remain as a distinct particle population that can be seen in for example, this New Horizons observed ion distribution. So the pickup ions follows a different component separate from the thermal solar wind peak. And so the pickup ion affect the termination shock, heliospheric termination shock, and so some of the pickup or the pickup ions from the solar wind can be transmitted into the heliosheath across the termination shock, and they are getting heated by the shock, and they become an important part of the heliosheath. And so there have been many simulations studying the pickup ion shock interaction, and an example is here from the Ziegler et al. And they show that using multi-fluid simulation, the model can only match the Voyager observed shock structure when you include the pickup ion population. And there are also many kinetic simulations, for example, here by Shrestha et al. And you can look at the more detailed kinetic physics at the shock, for example, the reflection of pickup ions. And so another thing that I want to point out is that so in the heliosheath, there's a different pickup ion population. So that's what we call the injected pickup ions. So these are a little bit lower energy, about 0.1 keV. And so these are the pickup ions that are continuously created in the heliosheath. And that's downstream of the termination shock. And so this is different from the transmitted pickup ions. So the transmitted pickup ions are created in the supersonic solar wind and then cross the termination shock into the heliosheath. And the injected ones are created within the heliosheath itself. And so this creation of newly injected pickup ions also affect the heliosheath, and that leads to the spatial inhomogeneity of the heliosheath. So the plasma parameters can change dramatically within the heliosheath from the termination shock to the heliopulse. And for example, here in the third panel, so these are some global heliosphere simulations, and you can see the plasma beta is changing from about 10 near the termination shock to maybe 0.2 near in the tail region. And also the fraction of these injected pickup ions are basically increasing from 0 at the termination shock and all the way to practically 100% in the tail region. Basically, they are basically replacing all the other ions. And so there are also large-scale structures, such as the heliospheric current sheath, that can affect the plasma condition. For example, in this second panel, it shows so it suggests that the reconnection at the heliospheric current sheath can basically deplete the magnetic field in the so-called sector region of the solar wind, and that leads to lower magnetic field. And there's also the heliospheric jets in the polar region that may be associated with some instability, and that also cause some local enhancement or the reduction in the magnetic field in this case. And so this is some recent work from one of the BU students. And so this basically means that there are many interesting plasma regimes to be studied in the heliosheath. And another interesting point about the heliosheath is that the flow is subsonic. And so that's interesting because then the fast magnetosonic modes can be reflected back toward the sun. And so this is the unique region, and the only other places like similar thing can happen is like within the Alfvén critical points near the sun, and that's where you can have reflection of Alfvén waves, and that due to the local gradients in the Alpine speed. And so I steal the figure from Ben Chandran here, and that shows the wave reflection near the sun. So essentially in the Heliosheath, we can have some similar process, and that's shown in this global simulation from another DU student. And so this is a spatial temporal plot, so the space in the vertical direction, and basically we see these structures in the Heliosheath. That's essentially the outward propagating solar disturbances that's propagating from the termination shock to the heliopause. And if you look at it, we can also see some of the structures may have negative slopes, and that correspond to reflective structures, and the reflection is mostly happening near the heliopause. And so of course, the difference between this and the inner heliosphere is that these are much larger time scale and larger spatial scale. So these are years and many AU. And also the Heliosheath flow is still mostly superalphinic because the termination shock is a fast shock. And so the alpine wave are probably still not going back toward the sun. And maybe unless in some special regions, like in the simulations, you can see there's maybe some regions with subalphinic wind, but it's not confirmed in observations, so it's still debated. And so another maybe related to the fast magnetosonic waves is the turbulence. So we see the turbulence observed by Voyagers is compressible. That means that it observed similar level of fluctuations in the 3 magnetic field components. And that's showing this Balaga et al. Paper that shows the distribution of the magnetic field. And all 3 components are similar, and also the magnitude of the magnetic field. And of course, another thing that Parker Solar Probe also ran into is the issue with Taylor's hypothesis. And here, similar, when we have wave speed comparable to the flow speed, like in Parker, we have the flow speed comparable to the Alpine speed. Here, it's comparable to the fast mode speed. We also run into the issue of Taylor's hypothesis, but if we try to take that into account, it was estimated that the fast mode has about 1/3 of the Alpine wave power. That's done by this recent work by Ling Zhao et al. And so this is still highly compressible compared to the inner heliosphere, where the compressible modes are only about 10% of the power. And yeah, okay, so that's the introduction. And so another important observation is the energetic neutral atoms, which so many of you may be familiar with the IBEX or IMAP here. And so these energetic neutral atoms are created by charge exchange between the neutral atoms and ions. And the ions may be either thermal ions or the pickup ions. And the Heliosheath ions usually produce most of the so-called globally distributed flux, which is in contrast to this so-called ribbon structure, which mostly come from the interstellar medium. And so I'm going to mostly talk about this GDF here. And I'll just note that to contribute to the observed flux, the parent ion should have an inward velocity in the solar inertial frame so that they can propagate back from the outer cryosphere back to Earth so that they can be detected. And so an important observation is that there's a discrepancy between the observations and the ENA models. So that's shown in these figures. Basically, the models significantly underpredict the ENA fluxes in many directions and energies. And the most significant one is at these lower energies. So this is about 0.1 keV. So we call that the ENA gap. And there's also a little bit smaller gap at higher energy. So that's about 10 keV. And so I'm going to mostly talk about this low energy gap today. And so if you remember, I just mentioned there are two populations of pickup ions in the Heliosheath, and we still don't know which one of those two populations may contribute mostly to the ENA fluxes. That's because we don't exactly know what's the distribution of these pickup ions. And for example, this is illustrated by the Fusilia et al. Figure. And so, for example, if we assume that pickup ions follow a shell distribution, that's on the right figures here, then the main source of ENAs are the transmitted pickup ions. That's because the cutoff energy for the injected pickup ions are lower than the ENA energies, so they are not contributing to the ENAs essentially. But if we assume the pickup ions may follow a Maxwellian-like distribution, then the injected pickup ions can be the more important component. And so this is also shown in some of the more quantitative models. So here, there are a lot of lines here, but if you just look at the blue lines, so the blue solid line, so the blue lines are for the injected pickup ion contribution to the ENA fluxes, and the blue solid line is from the Moscow's group, and the blue dashed line is from the BU group. And basically the difference is in how they model the velocity distribution. So we see that by changing that, there's a big difference.
Question. I was very familiar with it, but can you explain a bit more about the background? Why, for example, like the share model, why this is based on what kind of background? I can understand you use the Maxwellian distributions for the share model. So,
okay. Yeah. So the shell model is, if I go back to the pickup ions, so the shell model is basically means that these initially created pickup ions have a certain velocity that's about the solar wind velocity in the solar wind frame. And so the shell distribution means that these pickup ions will fill this velocity shell in velocity space. So it's like a spherical shell, and I'll talk a little bit about that later. So there's a sharp cutoff at this velocity. So that's where, so that's where you see in these models, these injected pickup ions have a sharp cutoff. That's from the shell distribution. And so we see the difference between the two models just based on because of the difference in the velocity distribution. But regardless of the distribution, they are still much lower than the observations. And so one of the explanations for this gap is that there may be velocity diffusion that could explain some of it. And that's shown in this Sternstein et al. Figure. Basically, when they assume a kappa distribution at the termination shock and then put it put in some velocity diffusion, and by tuning the parameters of, for example, the diffusion coefficients, they can more or less match the observation, but that's only in the downwind direction or the tail direction. And so there's still a problem in the upwind direction that's shown recently from the Moscow group. And basically they include an absurdly high amount of velocity diffusion that's shown in this yellow line, but it's still not going to match the observation. So this is in the upwind direction, so this is the Voyager 1 direction. And so we try to think about this problem in terms of energy budget of the turbulence. So we assume, if we assume a steady state, then the energy dissipation rate roughly balance the cascade rate or the injection rate. And then we use Kolmogorov theory for turbulence and use the spectrum observed by Voyager. And then we can estimate the energy cascade rate. And then we can multiply this rate by the Heliosheath crossing time from the Voyagers. So the thickness divided by the velocity. And we can get an estimate for the total energy dissipation. And so we find that this number is comparable to the solar wind thermal energy density. So this means that the turbulent dissipation should be important for heating the thermal ions, but it's probably not so important for the pickup ions because the pickup ions are much more energetic. And so we basically try to confirm this with some hybrid kinetic simulations with kinetic ions and fluid electrons. And we inject turbulence continuously in the simulation, and we try to match the energy and the compressibility with the Voyager data. And we use the initial distribution from a previous simulation for the termination shock. We took the downstream distribution from that simulation. And so this is what we got. The left one is the initial ion distribution. The main peak is the thermal ions, and the pickup ions are these wings in this dashed line. And we can see the effect of turbulence on the right plot. And so basically the turbulence causes some heating and velocity fluctuation that's broadening the distribution. And the effect is that before turbulence, the transmitted pickup ions are the main ion population at 0.1 keV, but with turbulence, the thermal ions are heated enough that it's become comparable to the transmitted pickup ions at these energies. But still, if we look at the overall change in the phase space density, it's very minimal. So although there are some effects of turbulence, it's not going to help with the ENA problem very much. And so next, what we are recently looking at is, can we model the ENA fluxes directly from Voyager data? And so the motivation is that the previous ENA models are based on global heliosphere simulations, which don't always match all the observables from Voyagers. So for example, in this figure, we can see there's some big differences between the modeled quantities and the observational data. And so we want to see if we can model the ENAs from the Voyager data and see if there's any difference. And so of course, immediate issue is that the Voyager does not measure the pickup ions, and and those are the in the energy range of the IBEX. And so we need to model the pickup ion distribution. And so for the transmitted pickup ions, again, we can use the previous simulations from the shock, since those are consistent with Voyager parameters. But for the injected pickup ions, we still need to model them. And so we do that by considering the injection rate due to the charge exchange in the heliosheath. And that depends on these three pieces. The first one is the neutral distribution in the heliosheath, and we have a reasonable idea about what it may look like and from this previous work. And the second piece is the ion distribution, and in particular the thermal and transmitted pickup ions. And so those we know from Voyager data and also the previous shock simulations. And the third piece is the charge exchange cross-section, which we can get from literature. And so by doing that, we can calculate we can model the injected pickup ion distribution. And so for the Voyager data, we did some averaging and interpolation and convert it to time along the streamline. And then we noticed that there's an overall increasing trend in the density. That's the third panel here. And we interpret that as a compression in the heliosheath, and that and we can quantify this by a compression factor that's estimated by the observed density by Voyager and the expected charge exchange loss. And since if there were no compression, we would expect the density to go down because of charge exchange. And this loss is basically the injected pickup ion density. And then this compression factor will affect the ion distribution through an adiabatic heating or cooling process. And so this is similar to what you have in the Parker's transport equation. And so by doing that with Voyager data, we can estimate the injected pickup ion density. That's the orange line here. And then the total ion density is the green line here. And the blue line is the original Voyager data. And yeah, I think maybe I didn't mention this earlier, but the Voyager data is measuring mostly the thermal ions. So that's what we assume. And so then we can get the velocity distribution of the injected pickup ions. And so these are the distribution at different radial distances in the heliosheath. And we see that it's continually increasing with distance. So that's just accumulation of more and more injected pickup ions as you go further into the heliosheath. And closer to the heliopause, we also see a second peak at a little bit lower velocity, and that's because the flow velocity is continuing to decrease in the heliosheath, so that the newly created pickup ions will have a lower energy near the heliopause. And these previously injected pickup ions will be shifted to a higher energy, or so the distribution, the peak is shifted to the right because of the compression effect. So we have this two-peak structure near the heliopause. And so then we just try to convert that to the ENA fluxes. And again, it seems that this green line is the total flux. There's still a big gap here So basically, using Voyager data, we can still see this difference between the model and the observations. And further, we can also look at the low energy gaps in particular. So zoom into the low energy around 0.1 keV. And here I want to know that the blue line is the contribution from the injected pickup ions. And I also show a dashed line that's an upper limit that I estimated by using the peak of the distribution from this previous plot for all the energies. So this means that you can try to hit the distribution, but it's probably not going to go past this limit. And so we see that even this upper limit is lower than the observed flux at these lower energies. So this means that there's still a big challenge in explaining what's going on at these lower energies. And so far I've been talking about the isotropic distribution for the pickup ions, like the shell distribution, but there another interesting thing that we find that the pickup ions could also have anisotropy. And so this is, so the standard theory for pickup ions is that the initially ring beam distributed pickup ions are subject to the ion cyclotron instability, and those instabilities will then scatter the pickup ions, and that causes a so-called bispherical distribution that's illustrated in the left figure. And so the bispherical distribution is basically these dotted and dashed lines inside the solid sphere. And so those are centered at plus or minus Alfvén speed. And because this is the waves created by these instabilities are Alfvénic, so in the supersonic solar wind, the solar wind speed is much higher than the Alfvén speed. So that means that essentially the VA is almost zero in that case. So the bispherical distribution is roughly the same as isotropic spherical shell. And so that's why we think that in the supersonic solar wind, the pickup ions may have a isotropic shell-like distribution. And we can confirm that with a test simulation in this case. And we can see that basically if we put in initially a ring distribution just at the perpendicular to the magnetic field, then after some time it's scattered to almost isotropic shell. So that's the second panel on the left. But for the Heliosheath, the difference is that now the velocity is lower and it's much closer to the Alfvén speed. So we can actually see the difference between a bispherical distribution and the shell distribution. So that's shown in this third figure. And so the red line is the bispherical distribution, which what we see in the simulation is roughly following this distribution. But in this case, the scattering is weaker. So this bispherical shell is not completely filled. So it's still mostly at the perpendicular. The distribution is still stronger at the perpendicular direction. And furthermore, we can look at 2D simulation instead of 1D. And in that case, the scattering is even weaker. And it's also not going to a bispherical distribution. It's probably closer to a spherical shell in this case. And so we look at this further, and we consider some more realistic parameters for the Heliosheath, and we consider injection of newborn pickup ions at mu equals 0 or the 90-degree pitch angle perpendicular to the magnetic field, and initially following a broadened ring distribution. And in this figure, I show how the distribution changed in the simulation. And so basically, we see that the distribution does not go to the bispherical distribution or shell distribution. So it's only elongated a little bit in the parallel direction. So the parallel direction is the horizontal direction in this case. And so this can be understood by looking at the spatial distribution of these field quantities. Here I plotted the magnetic field and density, and it shows that these are compressible structures with density fluctuations and also anti-correlated between magnetic field and density. So these are signatures of the mirror mode, and these are also oblique. So these are oblique to the magnetic field. And we can also look at the frequency spectrum, and we see that it's peak at 0 frequency. That's also consistent with the mirror mode, and because they are non-propagating. So these show that the instability in this case is mirror instability instead of the ion cyclotron instability in the standard theory. So this explains why this is only seen in the 2D simulations, why it's different from 1D, since the mirror mode is oblique and the ion cyclotron mode is parallel. And so the effect of this instability is that it's much less efficient in pitch angle scattering, and so we can quantify this effects on the anisotropy, and we can estimate the phase space density at 90-degree pitch angle and how it's enhanced relative to an isotropic distribution. And we can estimate about a factor of 4 to 5 enhancement relative to the isotropic distribution. And we also see that it's basically saturating after some time in the simulation, so it's not dropping below that. And so that could have an effect on the ENAs. And so these are still kind of theoretical, but there are observational evidence for that. So Voyager did observe some compressive magnetic structures, and so that's reported before. And as these magnetic bumps or holes in these cases, so these are compressible structures with change in the magnetic field magnitude, but not much change in the direction. And so these have been interpreted as mirror mode signatures, but it's not clear that these are, so this may not necessarily come from the pickup ions, so they could be temperature anisotropy driven mirror modes. So since Voyager does not measure pickup ions directly, so we don't have a direct evidence for that. So at this point, I guess it's still just speculation, but it's an alternative explanation for that. And so now we try to incorporate this in the ENA flux calculation. And so by that, we can extend our injection rate calculation in V parallel and V perp according to the local magnetic field coordinates that's constructed from the Voyager data. And then we transform the neutral to that magnetic field coordinates, and then get the ion distribution, and then convert it back to the inertial frame to get the ENA flux. So after doing that, we can get so this is the anisotropic injection rate in V parallel in the horizontal direction and V perp in the vertical direction. And we see that the injection is stronger near the perpendicular direction. That's as expected, since just because of the Parker spiral is mostly perpendicular in the outer heliosphere. And so the right panel shows the injection rate, including the effects of compression. So there's some heating in that. So it's slightly higher energy. And since we are considering anisotropic injection, we should also consider the compression with the anisotropic effect. So that's just based on the adiabatic invariance or the CGL description. And so we can, because we have measurements in magnetic field magnitude and density, we can use the adiabatic invariance to calculate the compression in parallel and perpendicular direction separately, and then put that in the injection rate. And so this figure is what we get. And so if we compare this with the previous figure, we see that if we consider the adiabatic invariance, then the compression is mostly happening in the perpendicular direction. So it's because these are no stretch in the vertical direction, but not so much in the horizontal direction. And so what's the effects on ENAs? So the right figure is the ENA model with this anisotropic injection. And so we see there's some effect on the injected pickup ions, but still the effect is not enough. So it's only increasing the total flux slightly. And also this is assuming no pitch angle scattering at all. So in reality, we should probably also take into account the hybrid simulation with some level of pitch angle scattering, which will probably make the total flux lower than this. So the gap is probably even bigger than that. And so I think I'll end the story here, but so it's probably unsatisfying, but I think I just want to leave with the message that so I think the Heliosheath is still an interesting region to study these plasma physics, and there are still a lot of things to learn from that. And this ENA gap problem is still an unresolved problem. And there are some possible explanations or speculations at this point. There could be, for example, interstellar medium sources, and could be some effects of reconnection and some effects on the uncertainties of the solar wind velocity and neutrals. But yes, this will be the future works. And yes, I think I will just stop here.
Thank you, Senbei. Actually, just on your last slide, I was curious, and I'm also new to the so the IBEX observations, but it looks like maybe you mentioned before, there's sort of like an upper bound, I guess, based on the measurements compared to the models. Or is there some intuition why there's like 2 orders of magnitude or even 3 for the lower energies that IBEX lives here? Or...
Yeah, so the uncertainty on these data are higher at lower energies. So it's
bars, I guess.
yeah. So basically these lower two energies are not very reliable because I think so first these there are some contributions from the primary interstellar neutrons, so that's very low energy neutrons, and there's also some contamination from the Earth, the geocorona, and also maybe some Earth magnetosphere neutrons and Earth ENAs. That's mostly affecting the lower energies, and so that's caused them to have a big impact. And I think IMAP should contribute to this because they go out of the geocorona to L1, so that's an advantage.
I was wondering about the turbulent spectrum. You showed the observed spectrum some slides back.
Mhm.
Could you show that?
Yeah.
Yeah,
This
this one. So this is in the absolute spacecraft frequency.
yeah.
Is there a sense where you would have the kinetic scales, ion kinetic scales on that spectrum? And the reason I'm asking is usually at the kinetic scales, you would have some sort of steepening of the spectrum, and here you just see the flattening due to the instrument floor.
Yeah.
So just the ballpark, is this high end of the spectrum in the kinetic range of one of the significant populations?
Yeah, I don't think so. I think it's larger scale than the kinetic.
It's all fluid scale.
Yeah.
Okay.
Yeah, I think it's affected by the noise.
And in your simulations, you presumably introduce some kind of turbulence, right?
Yeah.
And that's also in the fluid scales in the simulations.
So not quite. So it's kinetic simulation. So we are how do I say? It's kind of like cheating here since we are doing a much smaller scale than the actual scale of the Heliosheath. So we can't really do that. So we just do a small simulation and we only try to match the energy injection and the compressibility, not the other things. For example, the simulation time is much shorter and it's a small scale simulation. So here is like 60 something DI. So it's barely getting into the inertial range, I guess.
The last slide, the IBEX data, could you please show the IBEX data?
This one?
Yeah, so this is in connection with the EMA gap, right?
Yes.
So the data you have chosen here, these are from IBEX low.
Yes.
And so these are 7. So are these in different 7 ESA steps? Or like what data points you have? Like what are these data?
I don't know the details since I didn't work on the data myself. So these are from these earlier ones. Yeah, so it's from this Gali et al. 2023 paper. And so they listed the data and uncertainty in that paper. So that's what I get, but I don't know the details. Yeah, it's same in this figure too. Yeah.
So regarding this gap that we see, could solar cycle play a role in this?
Yeah, I think there's some effect, but I think this effect is not that big and probably affect high energy a little bit more, but I'm not so sure. But I think it's definitely not big enough to explain this whole gap. And it's also seen in all the directions in the heliosphere, and so this is not just upwind or downwind; it's all direction.
I just had a quick question about your simulation, not about the various fluxes that I don't know a lot about, but you said you did a multi-fluid simulation with shock capture.
Yeah, that's
Did
done.
you, how did you do the shock capturing? And I wonder about how well that did in damping diffusion over time.
Yeah, so
Did the shock diffuse?
Not sure. I don't think so. So this is not my simulation. So this is by Ziegler et al. So these are another research scientist at BU, but
Okay.
yeah, he did that
Okay.
before I was here. So,
Okay.
but these are basically multi-fluid with I think it's 3 fluid with thermal ion, pickup ions, and electrons.
Yeah.
And I think they set up some probably like a shock tube, but with roughly matching the jump condition of the shock.
Yeah, the jump condition would like determine the direction of the shock.
Yeah.
Okay, yeah, and there's advantages and disadvantages, a whole bunch. Okay, so you do think they're matching jump conditions.
Yeah.
Okay,
And
to determine the direction, the speed of the shock.
yeah.
Okay.
And then so they see those structures downstream of the shock that's related to the I think it's related to the gyro period or something, maybe something else.
Yeah, okay.
There's some,
Okay.
I think it's fast mode waves that's related to the pickup ions specifically. So I think they have a separate pickup ion. So because of the two ion fluid, they have like in the single fluid MHD, the magnetosonic waves become 2 different modes. In this case, they have a higher frequency and lower frequency one, and so these correspond to some of these waves in the downstream.
Mhm.
I think somewhere earlier slide explained the background. There was it's in the process of having the paper where orientation was such that the vertical was starting from heliopop, termination shock. So it was 2 different color scales showing the negative slope. I think it's reflected wave.
Yeah.
Yeah. And I was wondering, well, I guess I wanted to hear an explanation one more time, and then the negative slope you explained could be reflected waves. And I wonder if you see like fainter, like other slopes corresponding to like harmonics or something corresponding to the distance scale. Just I don't know, just naively thinking in terms of us standing.
Yeah. So these are still some ongoing works by one of the BU students, and yeah. So these are so we explain it again. So these are the spatial temporal plots. So the vertical axis is distance. So here is roughly the termination shock, and so this is roughly the heliopause, and so time is on the horizontal axis. So we see this structure with positive slope. So that means it's going outward from the sun. So it's propagating from the termination shock to the heliopause. And the slope of this line is roughly basically the flow speed plus the magnetosonic speed. So that's So these are roughly the magnetosonic waves that's propagating outward. And I think I can also show some my backup side. So there are some other probably better plots or the clearer plot here. So here we also did some analysis by separating the different modes. And so in this case, if we just look at the fast mode variable, we can see it's more clearly going outward. And in this case, the reflected or backward propagating fast mode, it has a more clear negative slope. And we also try to look at the slow mode. So slow mode will be just roughly the flow speed because it's roughly perpendicular. So the slow mode is reduced to a non-propagating mode. And so that's shown here.
What about the mirror mode? Would you see any evidence of the mirror mode with this kind of diagram?
Yes.
Yes, you would. That would be actually, I think, very interesting too.
Yeah, so the mirror mode, so first it's much smaller scale than this.
Okay.
So it wouldn't be in these kind of simulations. And also, so it's roughly non-propagating. So if we can see it, it's probably something like the slow mode. I would say, so probably something like the right plot. Yeah, that's a good question. Yeah, I don't know if this answers a question or.
Yeah.
Maybe I'm wrong, but just curiosity, it seems that the outward mode is steeper, the slope is steeper than the reflective.
Yeah, so it should be because it basically the positive slope is solo mean speed plus the fast mode speed.
Any other questions?
Let's thank our speaker again.